I would like to introduce to you our distinguished guest speaker, Pete Theisinger. Okay. Pete will tell us about the story of the Curiosity rover. Obviously, we all know about this mission, and it's been in the news for quite a long time. And it had a successful launch last November, and it's obviously on its way to Mars. And Pete will tell us a little bit about the current status of the mission and a little bit of behind-the-scene information that I think is going to be really interesting. So if you're here tonight, you're really lucky because this will be a very good presentation. So let me tell you a little bit about Pete Theisinger. Pete is the program manager of the Mars Science Laboratory project at NASA's Jet Propulsion Laboratory. His prior positions have included Director for the Engineering and Science Directorate, Deputy Director of the Mars Exploration Directorate, Manager of the Mars Exploration Rover project, Deputy Manager of the Mars Sample Return project, Deputy Manager of the Systems Division, I think this list goes on forever, Mission Support and Development Manager of the Mars Surveyor Operations Project, Project Engineer for the Mars Global Surveyor Spacecraft Development Project, and Manager of the Spacecraft Systems Engineering Section. Okay, the list is over. Pete has been involved in the systems design and development of interplanetary spacecraft systems since he originally joined JPL in 1967 as an engineer in the payload integration section. He has worked on a variety of missions, including the 1967 Mariner mission to Venus, the 1971 Mariner orbiter mission to Mars, the 1977 Voyager mission to the outer planets of the solar system, and the 1999 Galileo mission to Jupiter. He has also been involved in system engineering training and has participated in course and training development for a variety of commercial organizations. Pete has been awarded the NASA Exceptional Achievement Medal for his work on the Mars Global Surveyor mission, and the NASA Outstanding Leadership Medal for his management of the Mars Exploration Rover project. Pete earned his Bachelor of Science degree in Physics in 1967 from the California Institute of Technology. He was born in Fresno, California. He's married with 4 children and lives in La Crescenta, California. Okay, so after this talk, there will be plenty of time for questions, and I'm sure you have a lot of questions. I cannot wait anymore to introduce you, Pete, so it's my pleasure to introduce you, Pete Theisinger.
Thank you. Thank you. Can you hear me okay? Yes. Okay. Let me take these. Nicola asked for a bio, and I sent him the bio I had, and I told him a note. I said, you can shorten this if you wish, and I wish he would have. The people on the wings, you might want to kind of move your chairs closer to us, get a little bit of a better angle for the screen. And you probably can't see because of the flag, so I'll move the state of California. A little bit. So, as Nicholas said, I am the project manager for the Mars Science Laboratory project, and I'm going to start out showing you a video.
Before Curiosity can explore Mars, it's got to get there first. The last stage of the launch vehicle gives the spacecraft a final push and spins it up for our 8.5-month cruise to the Red Planet. Ten minutes before hitting the atmosphere, the cruise stage separates and final preparations for entry begin. Hitting the atmosphere at about 13,000 miles per hour, the spacecraft begins to slow down. While slowing down, the spacecraft uses its thrusters to help steer toward the landing target. We throw off weights to rebalance the spacecraft so that it's lined up for parachute deploy. After slowing to about Mach 2, or about 1,000 miles per hour, we deploy the parachute to slow down even further. Once we're below the speed of sound, the heat shield separates and the spacecraft looks for the ground with the landing radar. Once we reach an altitude of about 1 mile, the spacecraft drops out of the back shell at about 200 miles an hour. It then fires up the landing engines to slow it down even further. Once we've descended to about 60 feet above the ground and are going only about 2 miles per hour, the rover separates from the descent stage. As the rover is lowered, the wheels deploy in preparation for landing. Once the rover is on the ground and touchdown has been detected, the descent stage cuts the rover loose. It flies away, leaving Curiosity safe on the surface of Mars. One of the first things Curiosity does after landing is to deploy the mast, which supports many cameras and instruments. Curiosity shoots a laser at an interesting target. This helps us quickly understand the kind and composition of that target from a distance of up to 30 feet. If the target, Curiosity can drive up and inspect it with the instruments and tools at the end of its arm. The drill on the arm allows us to grab some of that rock and deliver it to the laboratory instruments inside the body of the rover. Those instruments can tell us even more about the mineral composition, getting us closer to understanding whether life could have existed on Mars. Curiosity will be exploring the red planet for at least 2 Earth years, and there's no telling what we will discover.
We would never, ever land there. So as we stand here today, we're 171 days from landing at Gale Crater. We'll land at Gale Crater at 10:32 p.m. Pacific Daylight Time on Sunday night, the 5th of August. It'll be August 6th in the East Coast and August 6th UTC, so you may see the landing described both ways. So the science objectives for Curiosity, am I standing in front of anybody? Yell at me if I do. Is to explore and quantitatively assess a local region on Mars' surface as a potential habitat for life, either in the past or in the present. The objectives include to assess the biological potential by investigating inorganic compounds, any organic compounds we might find, biomarkers, and processes that might preserve them. One of the major issues with doing investigations like this is the fact that it's very difficult to preserve for long periods of time the compounds that you're interested in preserving. Almost all the stuff you're interested in looking at has some relationship to water in its past. Okay, and water is a tremendous oxidizing agent. And so you have to, in fact, get very special conditions in order to preserve the compounds. And that's one of the issues that we will discover when we land at Gale Crater, is how well we've picked the site that does that. We want to characterize the geology and geochemistry of the field site, including the chemical, mineralogical, and we can do isotopic composition. We want to investigate planetary processors, including the role of water, atmospheric evolution, modern weather and climate. And we are taking with us a rad instrument to measure a broad spectrum of surface radiation, including galactic cosmic rays, solar proton events, and secondary neutrons. And this was supported and funded out of the Manned Exploration Initiative for NASA, and so this is in support of the Manned program to characterize the environment at the surface. Yeah, go ahead. So the enabling capabilities when Mars Science Laboratory was put together was a long-lived roving robotic laboratory capable of visiting many sites. Okay, we'll show the family portrait of Sojourner from Pathfinder and Spirit and Opportunity in a second. But both of those missions were very short duration missions. Pathfinder, 90 days. MER was designed for 90 days, although it has, Opportunity has now lasted 8 years as of last month. And if you ask me why that is, I'll talk to you after in the question period. Phoenix, which landed near the pole, was also a short duration mission because it was going to run out of sunlight because it was so close to the pole. So this is the first mission that's really had an extended life period as part of the design parameter. They wanted it to last 1 Martian year, which is 687 days, a little bit less than 2 Earth years. And in doing that, visiting many sites. Okay. They wanted to access a wide range of candidate landing sites assessed by orbiting spacecraft. That wide range means latitude, and that wide range means altitude. Okay. Latitude is a design issue because of thermal constraints and power constraints. When you get away, I mean, Mars has seasons just like we do. Its axis is tipped about 23 degrees just like ours, and so it goes through the same 4 seasons. At the equatorial region, which we do happen to be going to, I'll talk about the selection process later. At the equatorial region, on summer afternoon, hot day, you'll get to 15, maybe 20 degrees centigrade. Okay. At night, you'll go down to minus 90 to minus 100 degrees centigrade. And the winter is worse. Okay. And so in order to to assess a wide range of latitudes, you had to have a power source that enabled you to keep warm. Hence the use of the radioisotopic thermal generator on the spacecraft. Okay. Altitude. Okay, the surface pressure on Mars is 6 millibars, 6 1,000ths of an atmosphere, Earth atmosphere. It is like landing at 100,000 feet. Okay, it's the worst of all possible worlds for a landing spacecraft because it's not a vacuum. It can't be ignored. You saw the video. We hit the atmosphere at about 13,000 miles an hour. Okay, but there's not enough to slow you down very much. The big issue is, can you get subsonic and get rid of the heat shield, therefore, because you can't get rid of the heat shield supersonic. You got to go subsonic, get rid of the heat shield, and have enough time to do everything you have to do before you hit the ground. Okay, and and the altitude on Mars goes from minus 6 kilometers in Hellas to plus 20 kilometers at Olympus Mons, and the whole southern hemisphere is at positive, what we call above zero. I'll talk about that in a second. Okay, and we don't have the capability to do positive altitudes yet because we just run out of time. We've got to find better, efficient ways to slow down. Okay, and bigger chutes aren't the answer, amazingly enough. Okay, so what NASA wanted was access a wide range of landing sites, which meant try to get the best entry descent landing system we could get for altitude and be able to solve the thermal problem for latitude. Okay. We wanted a broad and flexible payload, including advanced geochemical instruments used on Earth labs. The big step forward that this mission made was to ingest rocks into instruments in the rover in order to do geochemistry. Okay, that was a major step forward from Mars Exploration Rover Spirit and Opportunity. They wanted to acquire and process dozens of rock and soil samples. So that's having things that don't wear out, that if you have cells that you process things in, you have to have a large number of them. You've got to be able to roll long distances, that kind of thing. And an integrated science team and operations strategy, which is what was done on MERS, so that's not a tremendous leap forward. Next, please, Nicola, please. So here's the family portrait. This is the administration building at JPL. This is a Mars Pathfinder Sojourner rover, about the size of a large mailbox, about 20 pounds. Could not operate independent of the lander because it required the lander for telecommunications capability, et cetera. Okay. designed to last as long as the Pathfinder base station lasted, which was design life about 90 days. Here's Mars Exploration Rover. It's about 185 kilos, about 400 pounds. A very large lawnmower or a very small riding lawnmower. And it has 5 kilograms of science payload on it. Okay. Here is Curiosity, and these 900 kilograms, a metric ton. Okay, 85 kilograms of payload. Okay, major steps forward. A single instrument, alpha particle X-ray spectrometer, a set of contact instruments plus photography, contact instruments, photography, and sampling instruments. Next, please, Nicola. So here's the mission overview. We launched on November 26th of 2011 on an Atlas 541, and the injection into the interplanetary trajectory was almost perfect. There was a 0.2 sigma injection, which it was wonderful. So that means to us is that we didn't have to do the first trajectory correction maneuver early. There are rules on planetary protection where we have to keep the spacecraft clean of spores if it's going to Mars, and the launch vehicle, upper stage, is going the same place we're going. Okay, and it's not as clean. So that means that the interplanetary injection trajectory has to miss Mars by about 300,000 kilometers. And then we do the first TCM, trajectory correction maneuver, to basically move over to Mars. And because of that distance, we have to do that pretty quickly, usually about 15, 20 days out of launch. This time it turned out we could wait a month, which was good for other reasons. Okay, we arrive in 8.5 months in August. It's a spinning cruise stage. That's very important to the navigators. You'd know that. And we arrive at Northern Hemisphere summer, although the landing site we selected is very close to the equator, as it turns out. You saw we used guided entry and controlled power sky crane descent, and I'll describe that a little bit later. The landing ellipse is 20 by 25 kilometers. That's the dispersion, 99% footprint that we'll land in. Okay, now, the landing ellipse for Mars Pathfinder was almost 300 kilometers long by 15 kilometers wide. Okay, and that's because it was a ballistic trajectory. You just throw the rock in the atmosphere, and the atmospheric dispersion takes it where it goes. So it's a combination of 2 air sources, navigation at the top, atmospheric dispersions. MER landing ellipse was 85 kilometers long and 15 kilometers wide. It was smaller than Pathfinder simply because of the geometry of the interplanetary trajectory. We had no intelligence went into it at all. Okay, that was just the way it was. And as a result, if you look at where MER landed, Gusev Crater, for example, Gusev Crater turns out to be 85 and a tick wide. Okay, so we landed edge to edge inside Gusev Crater. This is a much smaller landing ellipse, 20 by 25, because we do guided entry. We'll talk about that. And because of that, it expands tremendously the places on Mars we can go to. Engineers want to land on billiard tables, okay, because they're safe. Scientists want to go to mountains, because topography is science, okay, hence the dilemma. We wanted to land within plus or minus 30 degrees latitude and 0 kilometers elevation or lower. We talked about the reasons for that. And we landed 900 kilograms. Surface mission, prime mission is 1 Mars year, latitude independent, long-lived power source, 20 kilometers range. Okay, so we have designed this thing to be able to rove 20 kilometers. And you'll notice that the landing ellipse is 20 kilometers in diameter or 10 kilometers in radius. That means that we can, by design, drive to places outside the landing ellipse. That was not possible on Pathfinder or MER, and you'll see the impact of that when we look at the landing site selection. Okay, 80 kilograms of science payload, acquire and analyze samples of rock and soil. It's a large rover, high clearance, greater mobility than Pathfinder or MER. Nicola, please. So I'll talk about overall mission complexity. I've already, I think, talked a little bit about that. You'll have to tell me to slow down because I do get on a roll here. Overall mission complexity, I talked about some of the differences already between Pathfinder, MER, and MSL. Schedule, as you know, we suffered a launch delay beyond the original opportunity, which was in 2009. Actually, the original opportunity was 2006. Okay, But in my previous life, when I was running the Mars Exploration Rover project, I took all their money. And so they had to move to 2007. And then in 2007, we just could not get everything done. We had some development challenges, and the complexity of this vehicle and the test program made it impossible to get everything done to the high degree of rigor we wanted to do by the launch opportunity, which was in October of 2007. And the opportunities to Mars, because of the way the planets align, come every 26 months, roughly. So if you miss 7, you go to 9. You miss 9, you go to 11. Okay? And the launch period is around 25 days. So every 2 years and a quarter, you have 20 days that you can get to Mars, roughly. We had issues with actuators, and I'll talk about that. We had challenges with sample processing. This is the first time we're actually taking a piece of rock and digesting it and processing it and handing it to an instrument to be analyzed. And we're doing it a few hundred kilometers away, remotely, in the kind of temperature extremes that I mentioned. Okay, very, very challenging kind of situations, and it showed because we had a lot of development issues with the sample processing, sample handling. As those of you who are in the business know, you learn a little, you write new requirements, you learn a little, you write new requirements, you shoot the engineers, you keep going. I'll talk about the new entry, descent, and landing system and instruments. Next, please, Nicola. And I need to get a glass of water. So this is entry, descent, and landing. That one. Thank you very much. May I? Thank you. So this is entry, descent, and landing. And as you saw, we come in and we separate the cruise stage. The cruise stage contains all the equipment you need to get to Mars, but you don't need once you get to Mars. So the equipment for the trajectory correction maneuver, some telecom equipment, we use solar array for power to get to Mars. All those things are on the cruise stage. We throw it away about 15 minutes out. We go through the maximum heating and deceleration, and then we go through guided entry. The way we get the small landing ellipse is we fly guided entry just like Apollo flew landing men from the moon. Okay? We throw away mass out here so that now the center of pressure and the center of gravity, center of mass of the vehicle are offset from each other actually. That means if we fly an angle of attack, we can generate lift. And that's what we do. We fly an angle of attack and generate lift, and then we rotate that lift vector in order to move left, right, and shorten or lengthen the landing profile. When we finally run out of speed, get down to Mach 2, we kick out the parachute, do the gravity turn, go subsonic, drop off the heat shield, and then when we get about a mile up and the radar's got the ground, we lower the descent stage and the rover together and power descent. Okay? We fly that last mile to the ground, and then at the bottom we throttle down, the rover separates, we deploy the wheels, we touch down at about 1/10 of a meter per second or so. The descent stage detects that because it's carrying half the weight all of a sudden. So the control law detects that. It cuts the cables, and it flies away about a half a kilometer to a controlled crash. We do not burn to depletion. Okay. Now, most people, that's a couple things. First of all, if you looked at the MER and Pathfinder entry, descent, and landing, it would look like this. Okay. You would fly into the atmosphere, you slow down, you kick off the parachute, and then you come down to the ground after the gravity turn. We fly this S-curve. Okay. You got to get deep enough into the atmosphere so the atmosphere can generate some lift while you still have speed. So that's why you go down quickly and then flatten out. Okay? And then you fly this profile as much as you can. Okay, now most people look at this system, particularly the sky crane in the end, and they say to you, what are you guys thinking? Right? Or are you out of your pick your expletive deleted mind? Okay? But the vehicle is too large for airbags. If you think about it, that makes some sense. These things roughly look like a ball. I mean, they're pyramids or whatever, but they're roughly the same size in every dimension. And as the vehicle gets bigger, The airbags, although you put airbags all the way around, you're always landing on the bottom. So the airbag goes up by the square of the dimension of the vehicle. The mass goes up by the cube of the dimension of the vehicle. And eventually you run out of stroke in the airbag and you can't protect yourself anymore. And at 900 kilograms, we are way beyond that point in time. Okay, so you've got to use propulsive descent. Once you've made that decision, you've only got two questions. Okay? Do I put the rover above the propulsion stage, or I put the rover below the propulsion stage? Okay? Remember, your goal is to put the rover on Mars. Okay? If, in fact, you put it above the propulsion stage, when you land, the rover's still not on Mars. Okay? It's a couple meters away from Mars. And that last 2 meters is a hell of an engineering problem with a 900 kilogram rover. Okay? You think of cranes, you think of bridges, you think of all kinds of things, all of which are too massive, complex, and heavy to do this. On the other hand, the rover is built to interact with the terrain. It's got a mobility system that handles the terrain. Okay? It's capable of doing that if you can land gently enough. So the question is, can I put together a control system that will do that? Okay? Sensor, a good enough radar, and good enough throttle propulsion engines to be able to do that. Now, people often ask about the pendulum mode, right? Don't you expect this? Because they've seen pictures of helicopters carrying things off on top of tall buildings. And the answer is, it turns out that that mode on this spacecraft is well within the control algorithm on the power descent stage. But in addition, the no atmosphere helps you. There's no mass flow. Okay? You can have a 50 meter per second wind, but if it's only 6 atoms going by, it isn't going to move the rover at all. Okay? Hence, this is the way it looks. Next, please. With some numbers, it is 7 minutes from the top of the atmosphere to the ground. You may have remembered on Mir there was the 6 minutes of terror. Well, this is the 7 minutes of terror. Okay, guided entry gave us the additional minute. We are about 11 light minutes away from Mars when we land. So when we first are sitting on the Earth seeing the vehicle enter the atmosphere from telemetry, it's over. Okay? Whatever has happened has in fact happened. There is a requirement that we do telemetry during this phase. That's born out of the 1998 failures when the 1998 lander failed to land successfully, and we didn't know why. Okay? We have some suppositions, but we didn't know. So the requirement since then has been to do telemetry. On Mars Exploration Rover, we did tones to the Earth. So we used big antennas from the Deep Space Network to look for X-band tones. We could get basically a bit per second that way. And it turns out that Mars Global Surveyor and Odyssey were flying overhead. Okay? And we used ultra-high frequency, UHF, to do relay. It turns out we're doing the same thing here. An accident of celestial mechanics and nature is that the science orbiters want to be at an orbit that's basically 2 o'clock, 3 o'clock in the afternoon. And the angle at which you enter the Martian atmosphere following this profile puts you on the ground about 2 or 3 o'clock in the afternoon. And so the only issue is to make sure they're overhead when you land. And that's a relatively low propellant cost to do that, particularly when we know very well when we're going to land even today, and they can adjust their orbits. Okay, so we do guided entry. Our L over D is 0.24. We use RCS attitude control, banking the vehicle, as I mentioned. The way we propagate this vector is we tell the spacecraft 8 hours out, you are here with respect to Mars. You are here with respect to where you're going. And then it uses the inertial measurement unit to fly a profile to the ground. Okay, that's the sensor it uses. Okay, the parachute, 2.5 meter reference diameter Viking geometry disc gap band parachute, larger than we've ever flown before, but the same basic geometry. Deployed between Mach 1.6 and 2.1, depending on what the guidance algorithm says. Every lander on Mars has basically, well, let's go back up. When Viking went to Mars, Viking did a ton of parachute experiments. And what they actually did was they shot parachutes out of the atmosphere, then turned around, and with rockets drove them into the atmosphere and deployed them. So they went up to Mach 3+. They actually melted parachutes with high Mach deployments. But that test sequence defined what was acceptable in terms of deployments of parachutes in low density, high Mach number regimes. And all the landers since then have always been inside that test envelope. Okay? So we don't venture outside that test envelope with this parachute. We have a 6th antenna, 3.5 Ka band Doppler altimeter, Doppler radar, and we'll show you pictures of that in a minute. We had to redevelop the Viking main landing engines. They're all throttleable. That was a very successful development. And then the rover is lowered from the descent stage on an umbilical device. Next, please, Nicola. So it goes together like a Russian doll. Okay, the descent stage and the rover get married together. We put the back shell and the heat shield enclosing them, and we throw the cruise stage on top. If you think about it, we are actually building and developing and testing 3 vehicles. Okay? There is the vehicle that gets to Mars. That's all of this. Okay? There is the vehicle that enters the Martian atmosphere and then lands on Mars. That's this and pieces of this. And then there is the vehicle that we leave on Mars called the rover that does all the science after we've landed on Mars. So the test program, the requirements program, all of that has to treat the 3 mission phases separately and test them separately and look at the vehicle in those along those 3 axes. Next, please, Nicola. So talk about payload. We have 10 science instruments. There's remote sensing instruments, MASCAM up on the mast. It's a stereo pair of cameras with color filter wheels. They are different focal lengths. One is 40 millimeter, I think, and one's 120 focal lengths. Originally, they were supposed to be zoom cameras, but in the middle of the project, in what some considered a not well considered descoping exercise, they were made fixed focal length. And then it turns out there's a member of the science imaging team whose name is Cameron. And when Avatar lost his attention, he asked if we could put the zoom cameras back on the spacecraft. And we tried, but we didn't have enough time to get it done before launch. And so we have the fixed focal length cameras. Mike Malin from Malin Space Science near San Diego is responsible for those. The ChemCam is the laser breakdown spectrometer, shoots a laser at the rocks, vaporizes the laser, looks at the excitation from that event in a telescope, and does spectrometry based on that. Consists of a laser telescope at the end, and then we run a fiber optic cable down into the instrument that's in the body of the rover. Roger Wiens was built by Los Alamos and by the French. The French contributed the box at the top. Okay, we've got contact instruments on the arm. One is the MOLLE. It's a very high resolution, short focal length, basically like a geologist's hand lens. It's a camera that can be used to look at the fine structure of the rocks. MER had a similar instrument. And the alpha particle X-ray spectrometer, which was contributed by the Canadians, is on there. And the APXS flew both on Pathfinder and on MER. Okay. Inside the body of the rovers, we have 2 analytical laboratories. The second one here is Chemin. It is the X-ray diffraction that you saw in the video. Basically, it shoots X-ray through a vibrating crystalline structure and looks at the diffraction to determine crystal structure. And then there is the sample analysis at Mars. It is basically a gas chromatograph mass spectrometer that does that with pyrolysis or without pyrolysis, and it has a tunable laser spectrometer that can look at atmospheric gases. I think one of the early results from this mission will be looking at the atmosphere and seeing if there's methane at the landing site. That's a big question at Mars. And then we have environmental characterization instruments. The MARTI is a descent imager. So once the heat shield comes off, we're going to get descent video, 8 frames per second, high-def TV, all the way to the ground. Okay? It'll take us forever to play the data back, but it'll be a tremendous movie when we get it. Okay? The REMS is contributed by the Spanish. It's up here on the mast. It's a meteorological station. It does temperature and pressure and humidity, not very much, and ultraviolet radiation as well. The RAD is the high-energy radiation instrument that was contributed by the Manned Exploration Directorate at NASA. And then the DAN is a Russian contributed instrument, and it's a neutron source. It shoots neutrons into the surface, and then looks at reflected thermal neutrons, and the energy change occurs because of interaction with hydrogen in the surface, which most people say you got hydrogen in the surface, you got water. So we can look for water about a meter below us. Now we're flying equatorial, so there's a real question whether or not we'll see water or ice a meter under the soil, but we're certainly going to look. You can see the wheelbase, 2.2 meters, the height of the deck, 1.1, and the height of the mast, 2.2. Next, please. So here's the payload, just to show you some pictures. The alpha particle X-ray spectrometer, the radiation detector, the MOLLE, which is the hand lens, one of the mass cams with the fixed focal length, and the descent imager. These three all have the same camera electronics, camera CCD system. They have different focusing systems, different optics, and different filter wheels if there are any. Next, please. This is the REMS in various pieces, and the electronics. This is the ChemCam. This is the unit that's on the mast with the laser and the telescope. This is the spectrometer unit that is connected to it by the fiber optic cable, and this sits inside the rover. Next, please. This is the SAM instrument, the Science Analysis at Mars, and you can see the scale here. This thing is yay by yay by yay. It is huge as science instruments go, and as you can tell in here, it's all valves and plumbing and pressure vessels, and it's a bear. So this is the high payoff instrument, but it's going to be, hopefully we'll get it all to work just fine. The Chemin is the one we saw, the X-ray diffraction experiment. Next, please. Show you some pictures of the hardware. This is the cruise stage in ATLO. ATLO to us is Assembly, Test, and Launch Operations. As we build the equipment, we put it into what we call the System Integration Environment. That is ATLO for us. And it runs the entire phase of system test at JPL, environmental test at JPL. Then we ship stuff to Florida. We try and take it apart as little as possible, but we do take it apart somewhat. And we put it back together in Florida and do a final testing in Florida, then mate with the launch vehicle and put it, and it gets into space. You can see that there's avionics on the cruise stage, the fuel tanks for the trajectory correction maneuvers, and the thrusters. The red covers are removed before flight, and they're to protect against handling hazards. You can see these panels around the cruise stage. We've got an RTG in the center of this thermos bottle that's putting out 2 kilowatts thermal all the time. And we got to keep the temperatures under control, and so we basically run a refrigerator. We run a fluid loop from inside the rover to the outside of the rover, and outside of the vehicle, and these are the radiation panels that radiate that to space. Next, please. The descent stage, you can see the 6 engines, 4 on each side. The rover sits this way in this view. The propellant tanks, this thing when loaded is about 900 kilograms, it's about the same mass as the rover. The vehicle when it launched was 4,500 pounds, 4,500 pounds when it launched. We've got avionics, X-band, telecommunications equipment, and then on this piece, although not mounted on this picture, is the radar on what we call the proboscis. So the radar sits on the descent stage and looks over the edge of the rover. Next, please. This is the radar, 6 beams pointed in various angles to get the Doppler and to avoid false positives and to be able to handle all the angles at which you're asking the radar to work. These are canisters. The actual antennas are very small phased array antenna panels. These are protective covers. The electronics are mounted on the back of what we call the surfboard here. And this represents the mounting interface to that proboscis I talked about on the descent stage. One of the problems you have with entry, descent, and landing any vehicle, any Martian vehicle, is how do you test it on Earth? We all believe in test as you fly, but you do the test, it's less like you're going to fly the spacecraft, but you can't do entry, descent, and landing on the Earth. Okay, you got the wrong atmosphere and you got the wrong gravity, and you can't get it started correctly. You got to start at 13,000 miles an hour outside the atmosphere, right? And so what you do is you construct a whole bunch of tests in pieces and then try and stitch them together through computer simulations, et cetera. Okay, you do arc testing on the thermal protection surfaces. You do drop testing with the separation devices. You do parachute deployment for strength and for deployment with the mortar. You do a bunch of things like that. And of course, you got to test the radar. Next, please, Nicola. So, and this is Dryden. This was out of Dryden. Okay, and this is the radar on the front of a helicopter. Okay, and at one point we actually put a mock-up rover below it so we could see scattering from the rover. And so this is handling the low altitude, low velocity portion of the radar envelope. So you fly over a whole bunch of representative Martian terrains in order to get, flat lake beds, rocky areas, bouldered areas, that kind of thing to characterize performance. Next, please. We also have to characterize the high altitude, high velocity portion. And so we put it in an F-18 and we pointed at the ground. Okay. There was a lot of discussion about who was going to get to ride in the back seat of the F-18. And they wouldn't let any of us go. One of the dives, they get about 6 seconds worth of data. But by the time they go in and get out, it's 20,000 feet in altitude. It's very impressive. And it worked. And unfortunately, you can't put all 6 beams in the pod. So you end up with a single beam radar. And you stitch things together simulation-wise. Next, please. This is the heat shield. It's a new material, Pika, was developed jointly with the MAN program. And the reason was we've used something called SLA for all the previous entries. And the entry velocity on this case was not that much higher, so it shouldn't have mattered. But because we're doing guided entry, we're flying with an angle of attack. And that changes the flow dynamics across the heat shield and causes higher temperature areas on the heat shield, as well as the fact this heat shield is larger. And so we had to go to a new material, Pika, which we did. You can see the gaps here, the joints, which get mortared up, like laying the tiles on your kitchen floor. One of the interesting stories in a world that has overruns and all these things is this material was built by a small company in Maine. Okay? They, on their own nickel, increased their capital, put capital money in to increase their throughput and train staff, delivered under budget, ahead of schedule, and had not a single quality problem. I wish I could have done the rest of it with them. This is the back shell, and the door here is for the putting on of the RTG. The radioisotopic thermal generator is basically inherits a lot of design features from RTGs that have flown on outer planet spacecraft, Voyager, Cassini, Galileo. But it is smaller in power, 110 watts electrical when it's loaded at the beginning of mission, and it's designed to use in a wider variety of mission contexts. Okay, it gets loaded at the very end when the vehicle is on the launch vehicle. Okay, we touch bases with it twice. There's a prototype and mass models and thermal models, but the real RTG is built by the Department of Energy, and it's built and finally fueled and stored in Idaho. And then it gets delivered to the Cape. They will not tell us the delivery schedule. They truck it, and it shows up someday. Hello, there you are. It's surrounded by rifles being carried by people. And then we get to touch it twice. We put it on very early to make sure that it fits, and so we don't get surprised late. And then after we're on top of the launch vehicle, about 8 days before launch, we put it on and plumb all the fluid loop plumbing to it through that door. Next, please. So here's the rover, Curiosity. It's white in a white room, which makes the contrast terrible. You can see the six-wheel rocky bogie system. This is what we've used on JPL rovers for a long time. The reason you use this system is it allows you to climb over tall obstacles. If you drive your car over rocks, your wheels will not go over anything bigger than a half a wheel diameter. Okay. This, on the other hand, will climb boulders bigger than the wheel very easily. Okay. You can see the arm. The arm is just like your arm and my arm. It's got a shoulder joint, an elbow joint, and a wrist joint. The shoulder joint's 2 degrees of freedom, just like yours and mine. The elbow is a single degree of freedom, and the wrist is a single degree of freedom. And then at the end of the wrist, there's a turret to bring various instruments and equipment into play. You can see the mast here. The mast is laying down. The RTG sits in this little space back here between these two white things. Those are heat exchangers. Okay, like I said, the RTG puts out 2,000 thermal watts and 110 electrical watts. We collect the thermal power on these heat exchangers and run fluid from the heat exchangers into the top panel of the rover, and also through plates on the side of the rover that serve as radiators. So that's our thermal control system for the rover, and it keeps the inside very close to 20 degrees centigrade. Okay, it's a very nice system. Okay, let's see, this is a differential, just like your car differential. This is the ultra-high frequency antenna. Next, please. So this is looking down at the top deck of the rover. Once again, you can see the heat exchangers back here. The mast is laying down. You can see the gimbal actuators for rotation and elevation here. We use what we call flex capsules, which take flat flex cable and run them in a spiral to provide cable management as we wind and unwind the mast equipment. It has a single actuator at the bottom to basically raise the mast once when we land. These are the two inlet places for the two instruments, the Kemin and the SAM. Next, please. This was one of the last system tests in Florida, so we're down in Florida at this picture. You can see here we're looking at the rover, we're toe in. The rover, didn't mention it on the previous one, but the rovers have steering actuators on the four corners, all independent, and we have drive actuators on each wheel. So there's 10 actuators associated with maneuvering, with mobility. They're very, we'll show you a picture of an actuator in a minute. They're very high torque. A wheel actuator will put out 500 foot-pounds of torque, which is a little bit more than your Corvette. You can see in this case, we're doing a system test, and we're using the cameras to look at the sampling equipment, which is on the end of the mast, and we'll look at that in a second. So you can see the shoulder joint, the wrist joint, the elbow joint, the wrist joint, and then the turret right here. There's a bunch of equipment on the, I always tell people they're really ugly when you see them, you know. There's a bunch of equipment on the front. These are organic check material. That's used as a control sample. It's basically doesn't have any contamination or anything in it. It's a very bland material, and we can take samples of that material as a control sample when we find something interesting on Mars to make sure we're not looking at something we brought with us. There's 4 cameras down here and 4 cameras equally in the back. In addition to the science cameras up here, there's a set of engineering cameras. There's a set of what are called navigation cameras on the mast, a stereo pair, and there's a set of 2 sets of stereo pairs of hazard cameras on the front of the back. When the rover drivers decide what path the rover is going to drive across Mars, they make that decision based upon what the navigation cameras have told them of what the scene is around the rover. The science cameras are very high resolution and very small field of view, so they're not very useful for planning driving. The navigation cameras, which are medium resolution, wider field of view, are what you really use for navigation planning. In addition, on this mission, different than was on the Exploration Rover mission, is we have an orbit around Mars now, Mars Reconnaissance Orbiter, which is a high-rise camera instrument on it, which is capable of doing 30-centimeter photography on the surface. 30 centimeters, okay? They could see you all from 100 kilometers up. And because of that, we're able to use that view in order to plan rover driving as well. Okay. The hazard cameras are used for the actual details of driving. There are many, many ways to command the rover to drive across the surface of Mars. But each of those ways require that the rover autonomously make sure that it's safe. So the hazard cameras are looking down at about 45 degrees and photographing a punch of ground that's basically a couple meters out and about this wide. Okay. It does a stereo map interior of the rover in the computer, and it looks to see if there's any hazards. Rocks I can't avoid, gullies, anything that might be hazardous. Okay, so I'm going to go over to Nicola, and so I take that picture, I say, everything's okay. And I take a picture, and I say, everything's okay. and I take a picture and I say, oops, something has now appeared that doesn't look too good. And I don't want to continue on this path. Okay? So I will turn a little bit, take a picture. This looks okay. Okay? Now I got to turn back to Nicola. Still doesn't look too good. Back over here. Looking better. Okay? Back over here. Now I can continue. And it basically does that. Obviously, it could get into a situation where it can't get out of, in which case it simply stops, and then when it wakes up in the morning and we talk to it, we will see it's not where it's supposed to be, and it will tell us why. Okay, we can do it in a variety of different ways. We can simply say, I want to go to that corner, and I don't care how you get there. Okay. We can say, I want you to go to that corner, but you go to here, 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 and here first. Okay. If the wheels begin to slip too much, it will stop in order to make sure we don't bury ourselves, okay, like I used to do with my car at the beach. Okay. Next, please. This is an actuator. Okay. This is a cold encoder, a brake, the motor. This little thing is the motor. This is all gearbox. Okay. Set of output bearings in the gearbox and the output resolver. And then these attachments are where the torque is transmitted to whatever load you want to go into. These were a development challenge. Remember that we wanted to go to wide latitudes, and we had thermal issues. Okay? I mean, we had thermal design constraints. Okay? Actuators, for the most part, are on the outside of the vehicle. So they get cold. And we wanted to basically minimize the amount of work we had to do to keep them warm. We had basically two sources of energy to do that. One is to use electrical heaters, and the other is to try and do some kind of fluid interface across the actuators, which we gave up pretty early because of the reliability hazards associated with that. So we believed that there was a small company development project that had made actuators that had the capability to be very cold operated because they didn't need lubrication. Combination of titanium plus a proprietary lubricating coating on the actuators meant we didn't have to do that, okay, which was a touchdown, okay. And so we built a life model, life development test model, and we tested it, and it didn't work, okay. And there was all kinds of explanations for why it didn't work. I have another side story to tell you about that. And so we built a second development test model, okay, using the fixes that we figured out from the first development test model. And it didn't work. Okay. So we went back to steel, and we went back to lubrication, which meant we had to keep them warm, which meant we needed a bigger battery, which meant we needed to run more heaters, which meant we needed more switches and cables. Okay. And we did that, after we were 2 or 3 years into this design. Okay. The result of which is that everything that needed an actuator, arm, antenna, okay, mast, sample processing box, all had to go through design modifications in order to now, utilize actuators that were somewhat similarly different. And so their test programs all moved to the right as well. One of the reasons why we ended up launching in 2011 rather than 2009. A story about test experiences on Mars Exploration Rover project when it started. We were using the airbag entry system from Pathfinder, but the rover was heavier. The landing vehicle was heavier. And so the question was, are the airbags good enough, okay, to handle the landing mass and the landing velocity? So we had some leftover Pathfinder airbags. And so we sent them off to Plumbrook, Ohio, which is this very large vacuum chamber, and you actually inflate the airbags in the vacuum chamber, and you pull them down with bungee cords onto this rock-infested slanted board and see if they survive. Okay, and they did not. And I was project manager at the time, and I said, this does not look good, but I was told by my engineering staff that not to worry, Pete, that the real reason was because that they had not been stored correctly. This material is very sensitive to ultraviolet radiation. We did not package them correctly like flight equipment, and so the material had degraded. And when we actually build the real airbags, and we'll do that in about 9 months, we will go to test them, and you will find that the real airbags work just fine. Okay? And so I did. You know the end of the story, don't you? Yeah. So I did that. I believe that story. and the next one's failed as well. And so we had to spend 10 kilograms of mass and a year development cycle to fix that problem. Nicola, please. So here's the robot arm deployed, and this is the equipment at the end. Next, please, Nicola. And most of the equipment on the end is sample acquisition, processing, and handling equipment. Okay, we can brush rock surfaces using a kind of a orbital sander, in a sense. We can place and hold the instruments in place. Okay, now that sounds really easy. Okay, but the fact is that you're doing it from a mobile platform. Not only are you doing it from a mobile platform, but the temperature range from day to night will shrink the rover by about 2 to 5 millimeters. Which means the preload you're putting on the stuff on the rock is not necessarily what you think it's going to be when you come back the following day. Okay. We acquire samples of rock or soil by a powdering drill and scoop. This is the drill here. Sieve samples into fines and deliver the material to the Anico labs. We have an observation tray on the front of the rover that we can put stuff on if we're not sure what's consistency or things like that. One of the questions we have is water of hydration. Although there's no real water on Mars, there's water of a hydration inside the chemical, inside the mineralogicals. And when we drill the rocks, the drill is a percussion rotary drill. My project scientist says, just like you can get at Home Depot. And what it does is it augers material inside the drill bit. And the worry is that in doing that, the water of hydration comes out of the minerals and causes basically to start getting gunk. Okay. And that can gum up the works, and since we're so far away from home, that's not a good thing to do. And so we put an observation tray out that we can kind of play with this stuff a little bit to see how dangerous it might be. And we can exchange drill bits. We carry 2 spares, and we can take off the one that we've got and put one of the spares on. This is not a protection against them wearing out. This is a protection against getting stuck in a hole. Okay. So you see here the MOLLE, the camera, the APXS, the equipment that does the sieves and the scoops and the portioners for the sample, and the drill. The way this is built is the drill is the backbone of this equipment. Okay, so it doesn't attach to an existing separate structure, it attaches to the drill. Okay, remember my actuator story. Okay, actuator schedule moved to the right. Drill schedule moves to the right. Okay, therefore the turret moves to the right. Okay, an object lesson for all of us and how integrated you really want to make the equipment that you're putting together. Next, please. So here's a picture of the drill. This is the drill bit, okay, and basically the motor assemblies and a whole bunch of stuff inside. Next, please. This is the Chimera, the part of it that does the sample processing and portioning. There's about 12 small motors and actuators in this thing in order to move material around. We do not move the material by picking it up and moving it. We vibrate the various pieces of it and use gravity to move things around. Okay, so we turn this thing and then use vibration and energy of vibration to move things around. Next, please. And this is the whole thing put together. This happens to be I think the engineering unit. These are mass simulators for the APXS and the MOLLE, and you can see the Chimeras over here. Next, please. How are we doing? Not too bad. Some more pictures. This is the descent stage. And you can see that we don't have protective coverings on it right now, and the reason is because they're doing this lift in order to get mass properties, and in doing that you don't want anything on the descent stage that's not part of the descent stage. You can see the radar over here, the engines. They're canted away from the rover to avoid impingement by plumes on the rover, and they're tilted differently in order to avoid plume concentration on the surface and drilling holes into the surface. Okay? Next, please. This is being put together. Here's the rover on the bottom with mobility all folded up, and we're putting these two things together. You can see the people in the clean suits. The suits are there much more to keep it microbe and spore free than it is to keep it dirt free. Okay, the clean room itself, class 100,000, is good enough for dirt free, but we want the people as sources of possible biological contamination to be kept clean. Next, please. This is the rover from the bottom with the wheels and attached to the descent stage. There's the descent stage radar. Here's the motor, 2 engine nozzles, 2 more up here, inside the back shell. So you're looking up inside the back shell in this picture. Next, please. And this is the heat shield being put on. At this point, the rover is suspended, the vehicle is suspended from the top. The heat shield material can't carry any load, so you can't put it on the heat shield. You got to hold it from the top. The rover and descent stage attach at the top, so it's very much like a bell with a clapper inside. Okay, next please. This is just showing a different view. Protective coverings on the solar array. They're doing some final cabling. These are all access doors to get to the joints between the heat shield and the back shell and in order to do attachments. I talked to you about having to throw mass away in order to change the center of lift and center of pressure. Well, we do that when we get to guided entry, but when it comes time to deploy the parachute, the guys worried about parachute deployment doesn't want the vehicle to have any angle of attack. And so we actually throw more mass away at the bottom to recenter the center of mass and center of pressure so the vehicle will have a 0 angle of attack when the parachute deploys. Okay, next please, Nicola. Okay, you got to do the next 5 quickly. Ding, 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 ding. One more. So that's how you rotate it. This is the way we launch. We're attached to the Atlas with the heat shield up. Next, back up 2. This is what the Martians will see. Next, please. What? It's like a flying saucer. It is. Next, please. Next one then. And this is the Atlas fairing. With the rover, you can see how small we are in the fairing. Although mass-wise, we're about as much as they can get to Mars because of the energy required. They encapsulate us in the fairing. This is only the top half of the fairing. The way the Atlas is put together is you got the Atlas core and then the Centaur. The bottom of the fairing goes around the Centaur, so the Centaur carries no fairing load. Only the Atlas core carries fairing load. And then this whole thing is delivered and then held up as the fairing, as we are attached to the adapter on top of the Centaur, and then the fairings are put together. Next, please. So let's talk about landing sites. The process by which NASA selects landing sites. There's 2 parallel processes. There's the engineering process, which evaluates the landing sites for safety from a vehicle hazard standpoint. Are they flat enough? What's the slopes? What's the altitude? All those kinds of things. And then there's the science selection, which is where would it be nice to go, and what kind of science can I do there? Okay, and we started out with 85, 35, then 50, and pretty rapidly necked down to 6. Okay, and the reason you do that is because each of the sites have to be certified. That means that we have to do stereophotography of the entire landing ellipse using orbiters around Mars in order to get accurate slopes and accurate boulder and rock counts. That's an awful lot of pictures, and we can't do a lot of sites as a result of that. So we neck down quickly to 6, and then we carry the 6 for a pretty long time, and then eventually we get down to 4. Okay, right here. And then when we slipped from 9 to 11, we said to ourselves, based on the science that everybody's doing, does anyone have a new site? And so we said, a new one? And as it turned out, everybody said no. So we ended up here with the 4 sites at the end that we started with right here. Okay. Remember what I said about the driving distance and the ellipse. Okay. So one of the features of 3 of the 4 sites is that the very interesting science material is outside the landing ellipse. You got to drive to get to it. Okay. That really opens up the possibility for the science you can do, but it presents the risk question of suppose I don't drive as far as I think I'm going to drive. Okay. How much will my science suffer? Next, please. So here's the breakup. We have the old sites. This is Viking 1 and Viking 2, Pathfinder, Spirit, and then Opportunity, and then Phoenix. And here are the four in white, the four potential landing sites for MSL. Eberswalde and Holden right next to each other. That's about 60 kilometers apart. Marth and Gale Crater. Next, please. Excuse me. So, all of these are fantastic landing sites. Eberswalde, here's the landing ellipse inside of Eberswalde, has a fossilized river delta. It's the best river delta on Mars. Okay? And river deltas are places where a bunch of material that came down the river are deposited. The way deltas work is the water comes out this long finger, and then when it falls off the end, everything falls right there. So out at the end of these things are wonderful places to go find material that came down the river, potentially organics. Okay, that delta is over here. So this is a go-to, what we call the go-to site, where you land somewhere in the ellipse and then you got to drive over here. This is Gale Crater. This mountain in the center of the crater is 5 kilometers high. Okay, it's like standing on the beach looking at Haleakala. Okay. It's all sedimentary. It's layers and layers and layers and layers and layers. You get asked the question, I got asked today, how did this mountain get in the middle of this crater? Okay. And it turns out that what happened was the crater arrived, and then this whole area was overlain with sedimentary buildup into a plateau. And then differential erosion occurred and left the mountain in the middle of the crater. So we land here, where it's nice and flat, and the important stuff is over here. And we would climb up the mountain as high and as long as we could. Any ideas that we would get to the top are misplaced. Okay. This is Holden. This is an alluvial system, so this is a lake. Doesn't really have a delta. It has inflow channels and a lake, and presumably left sedimentary kind of deposits in the bottom of the lake. This is the area of interest, and once again we land as close as possible to it, and we would have to drive outside. Okay, this is Marth. Marth Vallis. This is the oldest material of clay type material on Mars. It's very, very old. And if you think that that's where life is, maybe that's where you go. It has the benefit that you land right on it. You don't have to drive. Okay? You have to drive to separate out group number 1 from group number 2, but when you land, you're on the gold mine already. Okay? This is where we're going. Okay? From an engineering standpoint, they're all the same. They're equally safe as far as we're concerned as engineers. The science of this is considered a little bit better. The reason is this is the place in the baseball parlance where you're playing for singles and doubles. Okay? You know, going up these sedimentary layers, you're going to get real good science, and you're going to go across several boundaries. Okay? If you really were trying for organics, if that was the prize, and it is, but if that was really where you're going to put all the marbles, you go to Eberswalde. But if you don't find them, there's no single or double to be had. Okay? So it's a home run, or it's not a very good mission. So this is where we're going. Next, please. Just to show you how much of a billiard table it really is, it's pretty flat. This is slopes. You get up to maybe 20 degrees inside this. We can land on 30. So we're not pushing the system at all. You can see, as we drive out, we begin to get into these very high slope areas. This is basically a canyon system, very much like Zion would look like. Probably not quite as much relief, but very much like that kind of a system. And because we've got such good orbital photography, we are able to actually do traverse studies, didn't bring one with me, where we actually map out what a traverse would look like in these canyons, because we got that good stereo photography from orbit. Next, please. This shows what we hope to get at Gale. There, if we, it's a 99% ellipse, so you could land here, long drive, or you could land here. So you get fresh craters. The advantage of them is they expose subsurface material, which does not have a lot of time on the surface to be exposed to cosmic rays or ultraviolet. There's a material of high thermal inertia in the middle of this thing. There are very good spectrometers flying in orbit, and they can't tell what it is. And that means that it's either it's carbonates, because they're not sensitive to that, or it's dust covered, but not so dust covered that you can't see the thermal fingerprint of what's below. But it's something that has high thermal inertia and is pretty dense. And then this is the Florida Mound transition right here, and this shows a couple of drives that we might take up the mountain. Next, please. This is a very much exaggerated relief showing that at the bottom of the mound we've got clays leading to sulfates, and then up here it becomes not impassable. So if we actually got up here, we'd probably back down, come around, and try another path. Next, please. So where are we? We're in cruise. We launched on the 26th of November. The spacecraft has been very well behaved. We had one computer reset issue, which turned out to be a design idiosyncrasy with the processor that we're using, and we're able to fix that by adjusting registers in the startup ROM. So that's been done now, and so we're on our way to Mars. We've touched about 40% of the capability on the spacecraft. We have done the first trajectory correction maneuver. There are 6. Okay, their second one will be in about a month. The third one about 20 days out, and then 4, 5, and 6 occur 5 days out, 2 days out, and then 6 hours out. Now we don't plan to do 6, but the experience on the experience on the 98 orbiter, you may remember the famous English versus metric units issue. Okay, the experience on the 98 orbiter was you don't feel the Mars gravitational well until you're about 24 to 18 hours out. Okay, so if where you think you are with respect to Mars, based on the navigation, is not where you really are with respect to Mars, that's when you find out. And the problem with the 98 mission is when they found out, they could not construct a maneuver fast enough to be able to solve that problem. So they went into the atmosphere too deep and they burned up. So we have an emergency TCM-6 opportunity 6 hours out that we will practice for, so that if we fall into the well and we don't like where we are, we can do a Hail Mary and try and solve that problem. We are right here. Okay? We're a little bit behind Earth. Here's Mars. When we launch, Earth is quite a bit behind Mars, and then Earth's rotation, orbital speed will take it far in front of Mars, and we'll arrive over here someplace with the Earth over here. Next, please. Almost a lot of what you've seen, you could have gotten for free. Except for my witty commentary, you'd have missed that, of course. marsprogram.jpl.nasa.gov/MSL. Okay, help yourself. The video you saw is downloadable from that site, as is the launch and a whole bunch of other things, and as will be the landing. So join us all on the 5th of August. Stay up late on Sunday night. Tell your kids they don't have to go to school on Monday. Oh, it's August, not a problem. Try to avoid the Olympics, which were going on at the same time, and the political season, which will be going on at the same time. And that's my story, and I'm sticking to it.
While slowing down, the spacecraft uses its thrusters to help steer toward the landing target. We throw off weights to rebalance the spacecraft so that it's lined up for parachute deploy. After slowing to about Mach 2, or about 1,000 miles per hour, we deploy the parachute to slow down even further. Once we're below the speed of sound, the heat shield separates and the spacecraft looks for the ground with the landing radar. Once we reach an altitude of about 1 mile, the spacecraft drops out of the back shell at about 200 miles an hour. It then fires up the landing engines to slow it down even further. Once we've descended to about 60 feet above the ground and are going only about 2 miles per hour, the rover separates from the descent stage. As the rover is lowered, the wheels deploy in preparation for landing. Once the rover is on the ground and touchdown has been detected, the descent stage cuts the rover loose. It flies away, leaving Curiosity safe on the surface of Mars. One of the first things Curiosity does after landing is to deploy the mast, which supports many cameras and instruments. Curiosity shoots a laser at an interesting target. This helps us quickly understand the kind and composition of that target from a distance of up to 30 feet. If the target, Curiosity can drive up and inspect it with the instruments and tools at the end of its arm.
I would like to introduce to you our distinguished guest speaker, Pete Theisinger. Okay. Pete will tell us about the story of the Curiosity rover. Obviously, we all know about this mission, and it's been in the news for quite a long time, and it had a successful launch last November, and it's obviously on its way to Mars. And Pete will tell us a little bit about the current status of the mission and a little bit of behind-the-scene information that I think is going to be really interesting. So if you're here tonight, you're really lucky, because this will be a very good presentation. So let me tell you a little bit about Pete Theisinger. Pete is the program manager of the Mars Science Laboratory project at NASA's Jet Propulsion Laboratory. His prior positions have included Director for the Engineering and Science Directorate, Deputy Director of the Mars Exploration Directorate, Manager of the Mars Exploration Rover Project, Deputy Manager of the Mars Sample Return Project, Deputy Manager of the Systems Division, I think this list goes on forever, Mission Support and Development Manager of the Mars Surveyor Operations Project, Project Engineer for the Mars Global Surveyor Spacecraft Development Project, and Manager of the Spacecraft Systems Engineering Section. Okay, the list is over. Pete has been involved in the systems design and development of interplanetary spacecraft systems since he originally joined JPL in 1967 as an engineer in the payload integration section. He has worked on a variety of missions, including the 1967 Mariner mission to Venus, the 1971 Mariner orbiter mission to Mars, the 1977 Voyager mission to the outer planets of the solar system, and the 1999 Galileo mission to Jupiter. He has also been involved in system engineering training and has participated in course and training development for a variety of commercial organizations. Pete has been awarded the NASA Exceptional Achievement Medal.
The drill on the arm allows us to grab some of that rock and deliver it to the laboratory instruments inside the body of the rover. Those instruments can tell us even more about the mineral composition, getting us closer to understanding whether life could have existed on Mars. Curiosity will be exploring the red planet for at least 2 Earth years, and there's no telling what we will discover.
We would never, ever land there. So as we stand here today, we're 171 days from landing at Gale Crater. We'll land at Gale Crater at 10:32 p.m. Pacific Daylight Time on Sunday night, the 5th of August. It'll be August 6th in the East Coast and August 6th UTC, so you may see the landing described both ways. So the science objectives for Curiosity, am I standing in front of anybody? Yell at me if I do. Is to explore and quantitatively assess a local region on Mars' surface as a potential habitat for life, either in the past or in the present. The objectives include to assess the biological potential by investigating inorganic compounds, any organic compounds we might find, biomarkers, and processes that might preserve them. One of the major issues with doing investigations like this is the fact that it's very difficult to preserve for long periods of time the compounds that you're interested in preserving. Almost all the stuff you're interested in looking at has some relationship to water in its past. Okay, and water is a tremendous oxidizing agent. And so you have to...
For his work on the Mars Global Surveyor mission, and the NASA Outstanding Leadership Medal for his management of the Mars Exploration Rover project. Pete earned his Bachelor of Science degree in Physics in 1967 from the California Institute of Technology. He was born in Fresno, California. He's married with 4 children and lives in La Crescenta, California. Okay, so after this talk, there will be plenty of time for questions, and I'm sure you have a lot of questions. I cannot wait anymore to introduce you, Pete, so it's my pleasure to introduce you, Pete Theisinger.
Thank you. Thank you. Can you hear me okay? Yes. Okay. Let me take these. Nicola asked for a bio, and I sent him the bio I had, and I told him a note. I said, you can shorten this if you wish, and I wish he would have. The people on the wings, you might want to kind of move your chairs closer to us, get a little bit of a better angle for the screen. And you probably can't see because of the flag, so I'll move the state of California a little bit. So, as Nicholas said, I am the project manager for the Mars Science Laboratory project, and I'm going to start out showing you a video.
Before Curiosity can explore Mars, it's got to get there first. The last stage of the launch vehicle gives the spacecraft a final push and spins it up for our 8.5-month cruise to the Red Planet. Ten minutes before hitting the atmosphere, the cruise stage separates and final preparations for entry begin. Hitting the atmosphere at about 13,000 miles per hour, the spacecraft begins to slow down.
In fact, there's very special conditions in order to preserve the compounds, and that's one of the issues that we will discover when we land at Gale Crater is how well we've picked the site that does that. We want to characterize the geology and geochemistry of the field site, including the chemical, mineralogical, and we can do isotopic composition. We want to investigate planetary processors, including the role of water, atmospheric evolution, modern weather and climate. And we are taking with us a rad instrument to measure a broad spectrum of surface radiation, including galactic cosmic rays, solar proton events, and secondary neutrons. And this was supported and funded out of the Manned Exploration Initiative for NASA. And so this is in support of the Manned program to characterize the environment at the surface. Yeah, go ahead. So the enabling capabilities when Mars Science Laboratory was put together was a long-lived roving robotic laboratory capable of visiting many sites. Okay, we'll show the family portrait of Sojourner from Pathfinder and Spirit and Opportunity in a second. But both of those missions were very short duration missions. Pathfinder, 90 days. MER was designed for 90 days. Although it has, Opportunity has now lasted 8 years as of last month. And if you ask me why that is, I'll talk to you after in the question period. And And Phoenix, which landed near the pole, was also a short duration mission because it was going to run out of sunlight because it was so close to the pole. So this is the first mission that's really had an extended life period as part of the design parameter. They wanted it to last 1 Martian year, which is 687 days, a little bit less than 2 Earth years. And in doing that, visiting Mary sites. Okay. They wanted to access a wide range of candidate landing sites assessed by orbiting spacecraft. That wide range means latitude, and that wide range means altitude. Okay. Latitude is a design issue because of thermal constraints and power constraints. When you get away, I mean, Mars has seasons just like we do. Its axis is tipped about 23 degrees, just like ours.